Hey everyone, welcome back to 3 Deviations. In today's video, we want to introduce multivariable limits. So we spent the last video introducing the notion of a multivariable function, which was really fairly simple, but now we are going to introduce limits. Now these multivariable limits are going to be the basis upon which we build the idea of a partial derivative and the multiple integral, which we will discuss later on. Just like in single variable calculus, the multivariable limit is a very important tool that allows us to build a lot of the applications that we use for multivariable calculus, which is of course probably even larger than the swath of applications that we use for single variable calculus. Anyways, let's get started by discussing multivariable limits. So a limit of a two-variable function, these are the limits we'll be dealing with so far because they get quite convoluted as you increase your dimension. But of a two-variable function, if there's a function whose domain includes points arbitrarily close to a, b, then we say that the limit of the function as xy approaches a, b is L. Then we can write that in the notation the limit as xy approaches a, b of f of xy is equal to L, right? Because we're mapping an ordered pair over to a height, which makes sense. This notation, I will admit, is a bit clunky, but it's how it works, so we've got to live with it. And we define this more precisely by using an epsilon delta definition, such that if for every epsilon greater than 0, there's a corresponding delta greater than 0, so that if x comma y is in the domain and 0 is less than the square root of x minus a squared plus y minus b squared, is less than delta, then there exists some epsilon such that the magnitude of f of xy minus L is less than or equal to epsilon. Okay, so what do I mean by this? What I mean by this is essentially this is corresponding to some sort of circle up here, some sort of circle region. This is corresponding to some linear region. Now, because we are in an area where we're dealing with ordered pairs and a plane for input space as opposed to a line, we need to use a circle as opposed to an interval. So that's the difference between the multivariable epsilon delta definition and the single variable epsilon delta definition. We won't be dealing with epsilon delta just yet, and you'll see why right now. So now I'd like to discuss the validity of a limit. Now, finding if a limit exists in multivariable case is a lot harder than determining if it exists for a single variable case. In the multivariable case, you need to prove that it exists for every single possible way you could get to that limit. Now, on the xy plane, that's easy, right? So if I have the xy plane, and I've got my real number line, and I've got a function up here, or something like that, and I want to determine if a limit exists here, then I just need to determine that the limit exists on this side and the limit exists on that side. If I can prove that, then I'm golden, right? However, for a multivariable function, we're dealing with a coordinate space and some sort of surface. So, in fact, if I have a limit here and I want to prove it exists, I need to prove it exists if I come from every single possible way I could, from every single path. I need to prove that that is the limit I get. Because there are some cases where you get graphs where you'll get, something like this. It would be a cross-section might look like, it might look like this. And then you've got some sort of asymptoting thing down there. And then it peaks down or something and it peaks up. You need to prove from every single thing that these would be the same, and they're usually not. So if the limit as xy approaches ab of f of xy is equal to some value, L1, on some path C1, and the limit as xy approaches ab of f of xy equals L2 on a path C2, then the limit does not exist because this value is different than this value. So if you can prove that on two different paths the limit is not the same, then you've proven that the limit doesn't exist. So in fact, proving that a limit doesn't exist is a lot easier than proving that a limit does exist in the multivariable case. usually only involves taking 4 steps. Now we'll try an example to kind of show you how this works for proving that a limit does not exist. So let's find the limit as xy approaches 0, 0 of x squared minus y squared over x squared plus y squared, if it exists. So first, what we are going to do is we're going to determine the paths that we want to get at this limit from. Now, the two most easy paths that we can try are the x-axis and the y-axis, because that makes it really easy for us to determine whether our limit exists. So basically what we're doing is if I have my xyz plane, and I have my surface, and I want to get to this point, when I get to that point, and I'm approaching 0, 0, or I'm at that point, that's probably 0, 0. And what I want to do is I want to approach it first from this way, then I can approach it from this way. Then I can see if those both give the same value, and if they don't, then the limit doesn't exist. So let's try from the x-axis. So let this first path, C1, be the x-axis. So if I choose that to be the x-axis, well, that means that y needs to be 0, because at the x-axis, y is always 0. So then I'm only looking at f of x comma 0. So I plug 0 in for y here. Then I get x squared over x squared. And x squared over x squared is 1. As long as x does not equal 0, then you have an indeterminate. Okay, so now what we can do is we can determine this limit. So if x squared over x squared is always 1, then f of xy will approach 1 as xy approaches 0, 0. This is always 0 except for when x equals 0 along the x-axis. Now if we let C2 be the y-axis, then that will mean that I need to set x equal to 0, so I'll have f of 0 comma y. If I plug this into this and I set these equal to 0, then I get negative y squared over y squared, which is negative 1 as long as y is not 0. So thus, we've determined that this is not equal to that. So what we get is f of xy approaches negative 1 as xy approaches 0, 0 along the y-axis. So this means that the limit does not exist because this value here does not equal that value there. So we've determined that based from two different paths, our limit is different. So thus the limit does not exist. So usually it's as easy as finding both of these x-axis and y-axis paths. But what you can also do, and what you may need to do at some point, is maybe use a line with some slope to see if that gives you a different answer, because sometimes it will. Because sometimes x and y will give you the same result, but that does you no good. That just proves that for those two specific paths, it's the same. So you need to either find a counterexample to prove that it doesn't exist, or you need to go to the full epsilon delta definition to prove that it does exist, and we'll talk about that in the next video. But anyways, we can see what this looks like. Essentially, what we have here is our graph here. So here we've got the y-axis right there, and here we've got the x-axis right there. So as we can see, so we approach 0, 0 from the y-axis. We're going here, and then we're going down, and then we're getting to negative 1 about. But for the x-axis, we're going up here. And then we get to here, which is about positive 1, and then we go down. So you can kind of see that based on this graph, we can determine that the limit does not exist because there's this little difference in there, which would be undefined, and that's why our limit doesn't exist, because both variables approach a different set value. Right, anyways, in the next video, I would like us to discuss proving that a limit does exist with an epsilon delta proof. So we'll discuss that, and then we'll go into maybe some applications of these limits, and then we will introduce the idea of a partial derivative. But before that, we'll also discuss continuity fairly briefly. All right, thanks for watching. We'll see you next time. Bye.